This is lesson number 2 in chapter 8. We're in a series of chapters having to do with motion in a curved path. Like the last chapter, we talked about centripetal acceleration and centripetal force and angular velocity and angular acceleration. This chapter, we're more interested in things that are spinning about an axis or spinning around a hinge or spinning on an axle. Those would be our axes of rotation, different terminology for that depending upon what it is that is spinning. We also learned in chapter 1 about something called a torque. It was represented by the Greek letter tau, and it was equal to an applied force times the distance that applied force is from the axis of rotation, assuming that they are perpendicular to each other. If they're not perpendicular to each other, we had the sine theta in there in order to get the perpendicular component of either the force or the radius in order to calculate the torque. Now, some textbooks, particularly calculus textbooks, will call torque a moment. Now, the difference between torque and moment is all torques are moments, but some moments are a force times a torque arm when there is no twisting or spinning that takes place. So moment is a little bit more generic than an actual torque, which causes angular acceleration. Now, in this particular chapter, we're going to learn about something called center of mass. And some textbooks will use the word centroid as the center of mass. In other words, given any object, whether it is an object like a sphere or a cube or a rod or something like that, it could also be a very irregularly shaped object like a lump of clay or a vase or a cup or a bottle or a chair, just anything you can name. We would be interested in finding what single point in that object is the center of mass. By that, I mean all the mass that is below that point would equal all the mass that is above the point. All the mass to the left of the point would equal all the mass to the right of the point. All the mass behind the point would equal all the mass in front of the point. That would be the center of mass. Now, we're not going to worry about 3 dimensions in this chapter. We'll just talk about 2 dimensions at most. And before I actually get into a more detailed discussion of center mass or finding the centroid of an object, if you look at this picture right here, we have a 18-wheeler truck. You're looking at it from the back end. Maybe it's a moving van. And these dark things here are supposed to be tires, and it's going on a banked curve, and you're looking from the back end. Now imagine you didn't know better, and when you loaded up this truck, you put all the light, fluffy things at the bottom, the pillows and all the styrofoam and everything like that. And then for some reason, you put the more massive things up top, like all of your favorite anvils and barbells and your big chunks of lead, all the typical things you might have in your house. And that I'm being facetious there. Well, in that particular case, if the center of mass, if you packed it like that, the center of mass would be quite high. And when the center of mass is this high, the weight, if we draw the weight vector acting from the center of mass, you'll notice that the vector representing the weight of the truck is outside the wheelbase of the truck. This means this truck is going to topple over. Now, let's suppose you loaded the truck the right way, the way professionals would load it. And so if you did it that way, you would put all of your barbells and your anvils and your boxes of books, in my case, down at the bottom, and you'd put your light, fluffy stuff at the top. In which case, now your center of mass is lower in the vehicle, and if you draw your weight vector, the same length as the previous one, because the truck has the same contents in it, you'll notice that this weight vector is between the wheel base It's between here, right up here, I should say. And therefore, this truck is not going to topple over. It is relatively stable. So we're going to be looking at what we mean by the center of mass. So let's begin by focusing our attention on some amorphous blob of clay or putty or mud or some object that is very irregularly shaped. It doesn't have to be irregularly shaped. It could be something that is very predictably shaped, like a cube or a wheel or a sphere or anything like that. In any case, we're going to put it in an XY axis. So here is my origin over there, where X and Y are both 0. And you can imagine that this object has an infinite number of particles. And I'm drawing all these particles in red, but to save time, I'm not going to do an infinite number of them. And every one of them would have a corresponding weight vector. If all the particles are the same, they would all have the same arrow acting down. And so we could say then that the total torque acting on this object would be the sum of all the forces, where your forces are the mass of each particle times gravity. That would be the force of weight, the mass times gravity of every particle that makes up the object. And every one of those particles is a certain distance from the origin, And if we found the perpendicular components of all of those, for example, we could find the torque relative to the origin. But in this particular problem, we are more interested in the vertical distance to the x-axis as our position x in the problem. So we're going to be to get our torque, it's going to be our force of weight times the position above the x or below the x-axis. And what we would be interested in is, could we replace every single one of these small vectors and small torques with one single vector acting from one spot and accomplish the same thing? That one spot would be called the center of gravity, CG. And in a minute, gravity is going to cancel out, so we often use the term center of mass instead. Plus, as long as my object is not gigantic, like an irregularly shaped asteroid or something that might have a variation in gravity from one place to the other, the gravity is going to be the same everywhere, at least to 3 significant digits, and we can ignore the gravity. So sometimes we talk about the center of mass instead of the center of gravity. And I'll probably use those terms interchangeably as well during this screencast. So we would like to find what one single torque will accomplish the same thing as the summation of all of my torques. Where this would be where all the masses would be the same, gravity would be the same, but we would have x1, x2, x3, all the way up to x, billions and billions and billions. And that would give us the equation that you see right here. So on the left side, in the parentheses, we have our total mass times our which would be the sum of all the total weight, I should say. And in a minute, it'll be the total mass when I cancel out gravity. We have the total weight on one side times a single position above the x-axis. And then here's the summation of all of the particles on the right side. And you can see that the g's are all going to cancel. And we end up with an equation then without all of those g's. And if we're trying to solve for position x, the center of mass in the x-axis, later on we can do the y-axis and even the z-axis, but the center of mass as the first coordinate for on the x-axis, we're going to solve for that right here. And that means we're going to divide everything on the right side of the equation by the total mass that is on the left side of the equation. And we get this equation right here to find our position of the center of gravity, or we could call it the center of mass, because we canceled out the gravity. Now we can also do that for the y-axis. And over here you can see we can also do it for the z-axis if we wanted to have our 3 coordinates in 3-dimensional space. Again, we're working at maximum of 2 coordinates in a planar surface. So the center of mass and the center of gravity are exactly the same thing when g is constant throughout the object. And that'll be pretty much the case in this chapter. Now, another thing about the center of, when we do these center of mass problems, we need to know whether or not the material that we're trying to find the center of mass of is homogeneous and symmetrical, like left side equals right side, front equals back, top equals bottom, or not, because that can change the math a little bit. And we could, for example, find the center of mass of a rod, and that's if the rod is, and I'm drawing it down here, if the rod is homogeneous, same material throughout the rod, and if it is symmetrical, in other words, it's not shaped like this, then we can assume then that the center of mass is going to be at the geometrical center. We can say the same thing for a sphere. If the sphere is all made out of the same stuff and it's not an oblong or anything, the center of mass is going to be at the dead center of the sphere. Or if we were to talk about a cube, if the cube is made out of the same material, in other words, it's homogeneous, if you remember your chemistry, and it's genuinely a cube, then our center of mass is going to be somewhere, is going to be exactly at the center of all of these, of the cube itself. So that's what this sentence is all about. So let's look at an object that is homogeneous but not symmetrical over here. Let's say this is all made out of the same kind of steel, and we want to find its center of mass. Well, the trick is pick a point anywhere along the handle. For example, we'll pick point A, and let's attach a thread to that so it's dangling from a thread, from some support. And once that wrench is stationary and no longer moving, and you can see in this picture the left side has more mass than the right side does, which is why it's angled downward toward the left. Then if we were to take a plumb line, and I'll draw the plumb line in blue, and hang it from point A, and we've got a mass at the bottom of it. Carpenters use plumb lines in order to make sure that walls and posts and vertical beams are all perfectly vertical. You'll notice that that thread, as it comes straight down, creates a line, if we were to trace the line, on the wrench. So I'm going to go ahead and erase this part right here. And now we have a line on the wrench going from point A to point B. And now we're going to do the same thing again. We're going to hang my wrench from a different place on the wrench and let it dangle. And the shape of the wrench makes it convenient to do it from the very end of it, because you've got a nice hole here. And then let's say we take our plumb line and we attach it to point C, and we let that plumb line angle down here, and there's the weight at the end of the plumb line. And then we trace the line all the way down with a Sharpie or something like that. You will notice then that the old line from point A to B and the new line from point C to D intersect right here. This then is going to be our center of gravity or our center of mass. And indeed, if you were to pick another point, let's say you were to pick this point here or pick this point here and dangle it from a thread and let it tilt one way or the other. When it stops moving, hang a plumb line from it and draw the vertical line that the plumb line shows you. All those points will intersect at the center of mass. And that's how you can find the center of mass of an object. Just using basically a thread with a rock or something tied to the bottom of it. So the next time you're accosted by Al-Qaeda and they give you an irregularly shaped object, you should be able to find its center of mass to their amazement and live to do physics another day. Now, let's take a look at a problem. Find the center of mass of a system of objects. So here, in part A, we have 3 objects that are located on the x-axis. In part B, which you're going to get a chance to do on your own if you want to practice, is on the right side of the page. And we have 3 masses, a 5 kilogram, a 2 kilogram, and a 4 kilogram mass. And these 3 objects, we want to find their center of mass. What point would we need to hold, if these 3 objects were somehow connected by a weightless straw? Would you, and you took a thread and you tied it around the weightless straw, maybe there or there or there or there or there. Where would you tie the straw so that all 3 masses would still be horizontal and it would not be tilted in one way or the other? In other words, where is the center of mass with the same amount of mass on the right as on the left? So that it would be, I should say, not the same amount of mass, the same amount of torque on the left side as the right side. I think I said mass earlier when I was talking about center of mass, and that it should be the same amount of torque, left and right, top and bottom, front and back. So, in this problem, what do we know? We know that the masses are 5, 2, and 4. 5, 2, and 4. We also know that the 5 and the 2 kilogram masses are half a meter apart, and the 2 and the 4 are 1 meter apart. And if we're trying to find the center of mass, we're going to use the equation that we just derived on the previous page. And we're going to take our summation of, not torques now because we've canceled out the gravity. G is gone. So we're going to take the summation of our mass times positions for each of the 3 objects. And then we're going to divide by the total mass in the denominator. And so here's my 5 kilogram mass, my 2 kilogram mass, my 4 kilogram mass. And we're going to choose as our reference point the 2 kilogram mass. This works no matter which mass you choose, but let's pick the 2 kilogram mass because we suspect the center of mass is going to be somewhere in between the 5 and the 4 kilogram masses. Again, it doesn't matter which one you pick. The math will work out with the same answer, meaning the same distance. You end up at the same spot on the x-axis, but just different numbers based upon either relative to the 5 or the 2 or the 4 kilogram mass. But you're going to end up with the same spot on the x-axis. So since we're choosing as our axis of rotation the 2 kilogram mass, you can see that its position is going to be 0. The mass times the radius, the distance that the 2 kilogram mass is from the 2 kilogram mass, is obviously 0. And the one on the left is a half a meter to the left, and so we make that negative. And the one on the right is a meter to the right of the 2 kilogram mass, so that's going to be positive. And again, we're using the logical convention for all of you backwards thinking folk that going to the right is positive and being on the left is negative. And yes, the answer will work out if you reverse that for some weird reason. Now, all we have to do is do the math, and we find out that we have a positive 0.136 meters. And since our reference point was a 2 kilogram mass, we're going to go in this direction, 0.136 meters, which is probably going to put us, somewhere right about here as our center of mass. Now let's do part B. Take a look at part B. And how does the answer change if the object on the left is moved upward by 1 meter and the object on the right is moved downward by half a meter? So let's take a look at that problem. And you have to remember what I just said because we can't see the picture anymore. But we do know where the center of gravity is. And now when we go to plug in our numbers, we have our 5 kilogram mass is 1 meter above the x-axis. And our and we're doing this with the finding the y center, the y coordinate, and we know that the 4 kilogram mass right here is a half a meter below. And again, we're doing above is positive, down is negative, in case you're a backwards thinking person. And the 2 kilogram mass again is going to be 0. The total mass stays the same. And now we found the coordinate for our y-axis. So here's the coordinate for the x-axis. Here's the coordinate for the y-axis in part B. Now, obviously, now that you've done a few AP Physics labs, you're probably wondering, just what is the center of gravity of your lab partner? Now, by the way, you can also, simply by changing one number and find the mass of your lab partner using the same experiment. We could find the weight of your lab partner if we didn't know this, but we did know where the center of mass was. We could solve for the weight of your lab partner. But for right now, that's not what we're going to do. We're going to do the problem as written. Find the center of gravity of this person who is lying on a piece of wood that comes from this object right here. And we have a name for these objects that's called a fulcrum. You might remember a seesaw. A seesaw, an old playground piece of equipment, it would have a fulcrum in the middle, might not be shaped like a triangle, and one person would sit on one side, and another person would sit on the other side, and they could go up and down. This is called a fulcrum. Now, on the other side, we have a scale. And we are told that this scale is reading 350 newtons. And obviously, this guy is going to weigh more than 350 newtons. We're also told that the board is uniform. So that means we can assume that the center of mass of the board is the geometrical center of the board, and therefore we can represent all the weight of the board with one single vector acting down, and I would call it the F sub W of the board. That's the weight of the board. Now we also have the guy's weight, and we're just guessing where this spot is. We're told that the guy's weight is 715 newtons. We just don't know the position of the center of mass, or the center of weight. And that position, we're going to measure it like we measure all radii in torques, is going to be this distance right here. The perpendicular distance to the axis of rotation, which is that point right there. So, as we get ready to solve this problem, you will notice that the person's weight, which is represented by this vector right there, this person's weight, if there was nothing else around, if there wasn't a scale, if the scale wasn't there, and the only force acting was the person's weight, it would cause a clockwise torque. A clockwise torque moving in the hands in the direction of the hands of a clock. And you might remember from the last section that clockwise torques are negative. So that's going to be a negative torque. And you'll notice that the weight of the board is also going to create a clockwise torque, CW tau, and therefore it also is going to be a negative torque. Now we also have two positive torques, because over here you have the normal force of the scale pushing up, equal and opposite of the feet. And we're not worrying about the weight of the feet, because all the weight of the individual is wrapped up right here. So we have this upward force, and that was the only force acting. If we weren't talking about the weight of the person or the weight of the board, you could see that this normal force pushing up would cause a counterclockwise torque, which would be a positive torque. Now finally, there's another one over here. This one right here is the normal force of the fulcrum pushing up on the board where the guy's head is resting. Now, there is a normal force, but the torque arm for this force is 0. R equals 0, because there is 0 distance from the upward force to the axis of rotation, because of the fact that the normal force is on the axis of rotation. So my radius equals 0. So this is not going to create any torque at all. So now when we come down here and say that the summation of all the torques must equal 0, the torque caused by the fulcrum is going to be 0. The torque caused by the guy's weight is going to be his weight, his mg, mass times gravity, times the radius, or we should say the distance to the fulcrum. And we don't know what that distance is, so we're going to call it x. Now the weight of the board is halfway down the full length of the board. So we take the length of the board divided by 2. That's the r distance, the radius distance, or we could call it the x distance to the fulcrum for the board. And then finally, when we look at the scale itself pushing up, the normal force of the scale pushing up with some force F, it acts perpendicularly against, at a distance, the full length of the board from the fulcrum. So once we have that equation in place, the summation of all the torques must equal 0. In other words, it's at equilibrium, which is something we'll investigate in more detail in the next section of the chapter. And now all we have to do is plug our numbers in and make sure we pay attention to our negative signs. And when we plug our numbers in, we get 79 centimeters. That means that since this is my reference point, the origin, the left end of the board, this distance is 79 centimeters. All right, let's take a look at another problem. Now, I don't know about you, but I can't tell you how many times in the middle of winter I go to a nearby lake, and the lake is frozen over, and there are two people on the lake, and we'll give them names, Sherry and Bob, and they've got a rope, and they're lying on their bellies, and the rope goes from the one person to the other, and it passes over a hole in the ice. And they're staying a safe distance away from the hole. In any case, obviously, physics problems often involve ice because we want to ignore friction. But I don't have any other explanation for why these two people are doing this unless they've been put up to it by Al-Qaeda. In any case, I already said that. We're given the information about Bob's mass and Sherry's mass. And they're each 5 meters from the edge of the ice. And we want to find out in this problem, where is Bob at the time when they both start pulling on the rope, when Sherry, because Bob is more massive, Sherry is going to make it to the hole before Bob does as they go hand over hand pulling on the rope. Where is Bob when Sherry gets right to the end? And hopefully this is not Bob's intention to pull Sherry into the icy water beneath. So, this problem right here, by the way, is exercise 8.5, which you can do on your own. Now, this looks like a complicated problem, but if we use the center of mass equation, and we only have two objects, we have Sherry and we have Bob, so there's only two components to our numerator, and we plug in Sherry's mass times her distance from the edge of the hole. And again, we're calling this the positive side and this the negative side for everybody that is thinking in the normal way. And then when we think about Bob, this is Bob's mass, and he's 5 meters on the other side. And we are taking this as my origin, my 0 point on my number line. And now it's just a matter of plugging our numbers in, making sure that we pay attention to that negative sign. And we find out that the center of mass, this is part A, is 1.39 meters, and it's positive. And so 1.39 meters, moving in the positive direction from my 0 point, would be somewhere around, maybe somewhere around in here. And that would be the center of mass. Somewhere around in there, 1.39 meters is the center of mass at that moment. We're also ignoring the mass of the rope. Now, find Bob's position using the center of mass and the fact that Sherry reaches the hole first. So now Sherry is being pulled more towards Bob than Bob is being pulled towards Sherry, because Bob has the greater mass. Not because he's stronger. We don't want our young ladies in the classroom to feel like this is old-fashioned. And when we look at this problem, the center of mass is going to begin to change. And So here's Sherry's mass, and here's Bob's mass. And Sherry has now reached the negative 100 meter position right there. And where is Bob going to be? Well, Bob's position, we're going to solve for that. And we'll see that he is now at position 2.74. 2.74. So that means 2.74 is a little bit more than halfway. And so Bob has moved all the way up to there, while Sherry has moved all the way to there. And if you ever encounter a problem like this again, I would sure like to know in what context. So send me an email. All right, here's another problem, a system of rods. We're going to have two rods. They're going to be of uniform density. And let's say a little bit about density. You all know that density, sometimes we use the letter D to stand for density. The Greek letter for density is rho, R-H-O, the Greek letter R. And that's because D can also stand for distance and diameter. So we use the Greek letter. And you all know that that's going to be mass divided by volume. This is in 3 dimensions. Now, in 2 dimensions, we actually use sigma. And the area density, let's say we had a sheet or a surface, and the sheet doesn't have to be perfectly flat, or maybe it's a piece of linoleum or a piece of rubber or a trampoline surface. Some surface that doesn't have to be flat, it can be curved, in which case you'd end up using some calculus. But in any case, the density, to find the center of mass, you'd use calculus. But as far as the density is concerned, it would be the mass of that surface divided by the area. And that's for 2-dimensional surfaces. Now, we use lambda, the upside down letter Y. And remember, lambda is also used to stand for wavelength. You'll see that again in January. You remember that from chemistry. Here, lambda is being used for linear density, and that would be the mass of the rod or the line or something that is straight, like a baseball bat or something, divided by its length, the mass per length. And this is a uniform linear density. So again, the rod is going to be like this or like this, and it's not going to change shape, and it's going to be made out of the same material. It's uniform. And it's making a T shape. So coming over here, here is my T shape right there. This example you can do on your own. And we need to first of all find the mass of each rod. Well, finding the mass of each rod is pretty easy. If density equals mass over volume, you all remember from freshman physics probably that the mass, therefore, is density times volume. Well, in this case, we're talking about mass times the density, and we'll use the Greek symbol for the linear density, lambda, times the length, and they're using a capital letter L of the rod. So you can see that the mass of the 3-meter rod, that is horizontal, is right here, and the one that's vertical is right here. So here's the horizontal one, and here's the vertical one. Now the next thing we want to find is find the center of mass of each rod. Now in order to find the center of mass, if we look at the horizontal rod, the center of mass is going to be at the geometrical center, since it's uniform, which is at the 1.50 centimeter meter mark, and it's right on the x-axis, so that y-coordinate is going to be 0. And then for the vertical rod, which is 2 meters high, the center of mass is going to be halfway up, which is going to be 1 meter up, and it is also 1 meter from our origin, right there. So now we have the coordinates for the center of mass of each rod. Now, when we come to find the center of mass of the entire system, you can see that all I'm going to do is I'm going to plug in my masses, the 15 kilogram mass, and then the, let's see here, what are the masses again? I'm going to have to go all the way back to double check. 5 kilograms. Did I do that right? So when we go to plug in our numbers here, here's our, these coordinates come down and do these positions right here. And it looks like we have 15 and 10 kilogram masses. And that's going to find my X coordinate, 1.30 meters. And then my Y coordinate, we're plugging in the zeros and the ones right here. And there's my total mass here, 0.400 meters. And so that means the center of mass of this system is going to be going X 1.3 meters and then Y up 0.4 meters. So the center of mass is located there. Now, the interesting thing about that is the center of mass is located outside of the system. It is not in the system at all. Let me give you another example. Let's say we have a donut. Where is the center of mass of that donut? Assuming that the thickness of the donut is the same all the way around, and you have the same consistency of dough all the way around, the center of mass would be in the hole in the middle, not even in the donut itself. And as my mom would always say on my way out to school as a boy, as you wander on through life, brother or sister, whatever be your goal, keep your eye upon the donut and not upon the hole. Very wise words from my mom. All right, center of mass, motion. So Newton's second law, you recall, F equals ma. It is unbalanced forces that cause an acceleration. If you have a force that does not have an equal and opposite force, it is going to cause an object to accelerate. And we're going to apply that to this system. And so here's my total mass of the system times its acceleration. And it's going to be the acceleration of the center of mass. And it's going to be the result of the summation of all the external forces acting on the object plus all the internal forces acting on the object. Now, we should point out that internally, any object internally is at equilibrium. Your iPad, your water bottle, your pencil, these things internally are at equilibrium. Otherwise, there would be acceleration going on inside the object. So when we come over to the next page, the summation of the internal forces equals 0. They all cancel each other out. And we are left with this equation right here. That the acceleration, and cm, by the way, stands for the center of mass, not centimeters, is going to be the summation of all of the external forces acting on the object. Now, I will point out something. This is a tangent now, and that is that the center of mass of an object, when you throw it, is always going to follow a parabolic trajectory. Now, if you were to take like a hammer, where you have most of the mass at one end and less of the mass at the other end, this object is not uniform. Its center of mass is not at the geometric center. And even if it was, you would see the object go spinning around like that before it hit the ground. However, if somehow you were able to mark the center of mass on that object and take a video of it and just follow the center of mass would be a parabolic trajectory, just like we studied several chapters ago. And I do recall way back in high school physics, one of the few things I remember from good old Mr. Schmidt, and he got a piece of cardboard that was kind of irregularly shaped. Let's say it looks like this. It might have been styrofoam, though I don't remember if styrofoam was invented back then. And he put a light bulb in one spot on this irregularly shaped object that definitely was not at the center of mass of the object. It was just too far off to the side. And we went into the physics closet, and he had a strobe light flashing, and he took a Polaroid picture of it. And every flash of light caught this light bulb in a different position. And sure enough, when we developed the film, which only took like a minute, the light bulb, because it was not at the center of mass, created a pathway that looked like that. Now, if we move the light bulb, let's say the center of mass is, say, right about here. If we move the object, the light bulb, to the center of mass and take the same picture, you would see a nice parabolic trajectory exposed on the film where the light bulb travels, even though the red object is wobbling around that point. Okay, back to our story here. You might recall that one of the kinematic equations we learned way long ago was distance, that something travels, equals the initial velocity times the time plus 1/2 acceleration time squared. And if you were not starting at position 0, but instead were starting at some initial position, your final distance would have this equation right here. Well, that's exactly what we have right here. And it's in the form of a quadratic equation. And you might recall your other kinematic equations as well. And we can use these equations. And here's an example with an exploding rocket. So a skyrocket, and it's not a very big one, it's only 3 kilograms, pretty wimpy, and it's already at an elevation of 30 meters. It's going to be traveling 20 meters per second straight upward. When it explodes, it's going to explode into 2 pieces. If it was a bigger rocket, we could say that the one piece was the booster of the rocket that fell straight back to Earth, and the other piece was the part that kept on moving. And the first mass, of course, is going to go straight down towards the center of the Earth. And it's going to hit 1 second later. So we're going to equate the two equations, 8.3 and 8.6, together. Here's my one equation, 8.3, where you find the center of mass. And here is the other equation over here, which is the modification of our kinematic equation for finding position. And now we're just going to plug all of our numbers in. And remember that 1/2 of A, since A is acceleration due to gravity acting downward, again, negative down here, positive up here. So we have our negative sign. We find out that position X is going to be 67.7 meters. And let's see, at what height is mass 2? This is the height of mass 2. And that concludes this lesson.